Hey, and welcome to webinar number 7, all about the kinetic molecular theory, also called KMT, and gas laws. So this is one of the last parts of Unit 3. The only thing that's left is solution in Beer's law, which we'll do next week in webinar number 8. So just a reminder of what the kinetic molecular theory is. Gases are always moving, and they're moving in a very random motion. So imagine the room around you, and the gas molecules are just bouncing off the wall, bouncing off of you. And also remember that gases take up very little room. Atoms are pretty small. So if the gas molecules are really far apart, then that means most of the room is actually just kind of empty space. So while you do have gases in the room with you, the spaces between the gas molecules is just empty space. In the whole room, how much of the space is taken up by gas molecules? Very little. In order to get rid of complex calculations, we're also going to assume that there are no attractive and repulsive forces between gases, because obviously intermolecular forces and stuff like that are going to cause gas laws to go kind of wonky. And that when two gas molecules run into each other, that energy is transferred. So we think of this like, imagine a pool table where you hit a ball on a pool table and that the molecules are constantly moving. They never slow down. So when one pool ball runs into the other, they'll just bounce around and bounce around on the pool table. It's not like they slow down because of friction. And then the last thing we say is that the temperature is related to how fast the molecules are going. The real gas laws versus ideal gas law, well, we have an ideal gas law, PV equals nRT. And it makes the assumption that gases really don't take up room, and they also don't have intermolecular forces. And that's because if you want to do math with real gases, the ideal gas law would be much, much longer and really, really crazy. So how can you take any gas and make sure it's an ideal gas? What you do is you make it go high temperature, so really fast molecules, if they get close to each other, really don't have time for intermolecular forces. And low pressure, that's the same thing as saying gas molecules are really far apart. And if they're really far apart, then they don't have those intermolecular forces. So keep them really busy, going really, really fast, and keep them far apart. When we look at gas laws, we want to think about what is pressure really? And pressure is just the gas particles, since they're moving, and whenever they strike a surface, they exert a certain pressure. So that pressure is the force that they hit you with spread out over an area. If you put a 1 pound weight on your hand, you can feel that weight. But imagine that 1 pound weight in the form of a 1 pound pin pressing down on your skin. Well, it's on a much smaller surface area, and so we would call that more pressure. Obviously, if you take a gas and you make it live in a smaller space with a decreased volume, we get more pressure. The decreased volume causes more pressure because you've got more collisions because the gas molecules are closer together, and those collisions happen in a smaller surface area, causing an increased pressure. And obviously, if you heat up a gas, then the particles get faster. And if the particles hit harder, because they're faster, then of course they exert more pressure. So let's look at this gas pressure simulator for just a second. The molecules are bouncing around, and you can see that it has a pressure of 1 atmosphere. So let's look, how can I change the pressure based on KMT? Well, number one, I can add more gas. And when I add more gas, look, the pressure went up. And that's because more gas molecules means more collision. How else could I increase the pressure? Well, what if I made the whole container smaller? Notice that the pressure goes way up, and we say that they are inversely related. So as the volume goes down, the pressure goes up. And if we were to increase the volume, the pressure would go down. Those same molecules are colliding in a much less surface area, and that same amount of force of collisions hitting on a smaller surface area means more pressure. We can also take a stab at heating the molecules up. So if we make the temperature go up, you'll notice that we went from 325 Kelvin to 600 Kelvin. Notice that the pressure pretty much almost doubles. And we say that those two things are directly related. If the temperature in Kelvin doubles, then the pressure doubles as well. The last thing we need to look at is how fast are they going. Notice that gas A is going 1644 over here. That's its speed. So let's also squirt some gas B in there. Let's see if we can notice the difference. Notice that gas B is a much larger molecule than gas A. But notice that their kinetic energies are the same. That's because they're the same temperature. So two things that have the same temperature are going to have the same kinetic energy. And then notice RMS means the root mean square velocity, or in other words, how fast are the molecules going. Molecule A is going 1644, while molecule B is going 503. So what we can get from that is bigger molecules move slower and smaller molecules move faster. And that's necessary because they have the same kinetic energy. Kinetic energy is how much energy it has when it hits you. So if you're a really tiny molecule, you have to be going faster. And if you're a bigger molecule, you're going slower. There are a couple gas laws we need to think about and then use for AP chemistry. The first one is the combined gas law. PV over T is equal to PV over T. You probably remember this from chemistry class. It's a simple plug and chug. The only thing is the temperature always has to be in Kelvin. So if you know the pressure, volume, and temperature under one set of conditions, and you change, say, the pressure and the temperature, then you should be able to find the new volume. It's pretty much just plug and chug. The second gas law is that of Avogadro's law. It sounds really complicated, but it's not. It says that the more gas you put in something, the bigger volume it's going to have. Or the more gas you put in something, the greater the pressure it's going to have. So you blow more air into a balloon, it gets bigger. That's pretty easy. Or you put more air into a tire and the pressure goes up. The ideal gas law is the one that's on the AP reference sheet, and it's the one that you need to worry about most all the time. Your units have to match. So that gas constant R is on the formula sheet, and you just need to look at the units. If it says liters, then the volume has to be in liters. If it says atmospheres, then the pressure has to be in atmospheres as well. And temperature always has to be in Kelvin. So just make sure you're paying attention to the units as you go. Other than that, it's really just plug in the ones you know and find the one you're looking for. Sometimes they'll ask you to find the density of a gas. So we can take the ideal gas law, PV equals nRT, and instead solve it for N. And we know that N, the number of moles, is equal to the mass divided by the molar mass, right? We can find moles, which means the molar mass is equal to the density times R times T over P. A good way to remember it is molar mass cat puts dirt over its P, like a litter box. So if it ever asks you to find the molar mass of an unknown gas, then you're looking for, density, that's right. And the density has to be in grams per liter because R is typically in liters, has a liter unit somewhere, and molar mass is grams. So just make sure it's in grams per liter. This is called a Maxwell-Boltzmann distribution. So if you look at the molecule and think about what I showed you earlier in that gas tank when we heated up the molecules, you can see that the x-axis down here is the speed. That's in meters per second. The number of particles is on the y-axis. So what I want you to know is there's the same amount of gas in each one of these curves. The light blue peak is higher because there's a smaller range which the molecules can live in, from 0 to, say, 1,000. So, of course, there's going to be more molecules within that range. Now, if you spread out those same molecules and say, now I can make them live at a speed from 0 to 1,500, or from 0 to 2,000, or from 0 to 2,500, that peak gets lower and lower because those molecules can inhabit a greater number of speeds. Now notice, some of the molecules are going 0 and some of the molecules are going really fast. We would say the average speed is right here at the middle of the peak. And if you're looking at the middle of the peak, that's about the average speed of the molecule. So looking at the graph, what happens to the average speed of the molecule as you heat up the gas? That's right. As you heat it up, the average speed gets faster and faster because it grows along that x-axis. So imagine as it gets warmer, taking your hand and pushing down on the light blue peak. And when you push down on it, it squeezes it out to the right. And if you were to take the red peak and push it with your hand from the right-hand side, so you're on the right-hand side, and push it with your right hand, that peak would be pushed to the left and it would go up. So notice that connection between hotter temperatures is faster molecules. We could do the same thing, except let's keep them all the same speed. Remember back to the box that I showed you a little while ago. I had gas A and gas B. Remember, one of the molecules was bigger and one of the molecules was smaller. And also remember that one of the molecules was faster and one of the molecules was slower. So what can we gain from this? Well, if we look at all the noble gases, helium, neon, argon, and xenon, we can see that helium is the fastest molecule. We know that because it goes from 0 to 2500. So those molecules are really, really fast. And that makes sense because they're the smallest molecule. Xenon would be the slowest molecule because it weighs the most. You won't have to calculate how fast they go. You just have to be able to read and interpret graphs. When you have a mixture of gases, we can actually talk about the partial pressure of each gas. So in this time of COVID, you may have heard of something called a pulse ox. So in your bloodstream, how much oxygen do you have in your bloodstream? And they can do that based on partial pressures. It's not that you just have oxygen in your blood. You've got carbon dioxide, nitrogen, and other gases. But we can talk about just what the partial pressure of oxygen is in your body. So if you had 20 molecules of A and 40 molecules of B, and the mixture has a total pressure of 30 millimeters of mercury, what is the partial pressure of A? Well, A was 20 out of a total of 60, so 20 out of 60 means that it's 1/3 of all the molecules. And since it's 1/3 of all the molecules, then it's 1/3 of the pressure. So if it's 1/3 of 30 millimeters of mercury, then that means gas A has a pressure of 10 millimeters of mercury. Gas B is 40 out of a total of 60, and that means it's 2/3 of the total pressure. If you took the partial pressure of each gas and you added it all up together, then you would get the total pressure. So if the pressure around you right now is, let's say, 758 millimeters of mercury, you could find the partial pressure of each one of the gases, carbon dioxide, nitrogen, some helium, whatever gases are in your room, and we could add those up and it should come to that total pressure. Oftentimes in chemistry, we will actually collect gas over water. That means in a chemical reaction, the gases get made, and then we have to make that gas travel through a hose or something, and it gets put inside of a bottle that's full of water. And when it's full of water and the gas goes up inside, then the water gets pushed out. So the thing to keep in mind when you collect a gas over water, so imagine a bottle and it's upside down in a container of water. The gas is not just the gas you're collecting, it's also got some water vapor. So if you have a bottle of, say, hydrogen gas, know that it's also got some water vapor in there. So if we know the total pressure is, say, 100, and we know the pressure of the water vapor because we looked it up, then we could calculate the partial pressure of the hydrogen. So let's just make up some numbers. The total pressure is 100. The water vapor is 7. So what is the partial pressure of just the hydrogen gas in the bottle? It would be 100 minus 7 is 93. Here we see that setup. So we've got some potassium chlorate, we heat it up, it makes oxygen, and the oxygen goes up inside the container. But remember, that's not pure oxygen. There's also some water vapor. So we always have to subtract out the water vapor. So here's a kind of question that you may see. You got 3 gases. Each of them is at the same temperature: neon, argon, and oxygen. What is the correct identification of each gas? So they're either going to ask you about the same gas at different temperatures, or they're going to say 3 different gases at the same temperature. And this is that latter choice. So since they're all the same temperature, I'm not worried about temperature. So out of neon, argon, and oxygen, we need to know which one will be the fastest and which one will be the slowest. So if you look, graph A has got the tallest peak, and it's the farthest over to the left. And we say the average speed is right here in the middle. And if it's right here in the middle, then we know that it must be the slowest gas because it's got the lowest velocity. That means gas A must be the slowest gas. So out of neon, argon, and oxygen, you need to figure out the molar mass of each one, because the bigger the gas, the slower the molecules. Conversely, the smaller the molecules, the faster the gas. So neon comes in with a molar mass of about 20, argon comes in with a molar mass of 40, and oxygen, since it's O2, comes in with a molar mass of 32. Since argon is the biggest, that means argon must be the slowest gas, the biggest molecule. So if we look, both C and D are good choices because they both show argon as being the slowest gas. So who should be faster? Should it be neon or oxygen? Well, neon has a molar mass of 20 and oxygen has a molar mass of 32. That means that neon should be the fastest gas. And so choice D is right, where graph C is the farthest over to the right and has the highest average velocity or speed, and thus that must be neon. Sometimes the AP exam doesn't ask you to actually do math. Sometimes the AP exam says, hey, what's the correct setup for the math? You'll see this on the multiple choice oftentimes, because the multiple choice, you don't get to use a calculator. So if you go from 3 liters of air down to only 0.5 liters of air, what is the new pressure? Well, if you're going from 3 down to 0.5, that means the volume gets smaller and smaller and smaller. And we know that the smaller the volume, think back to the box I showed you before where I pushed down the plunger on the gas, the smaller the volume, the greater the pressure. But how much greater is the pressure? Well, if you're going from 3 liters down to 0.5 liters, then the math is 3 divided by 0.5. And 3 divided by 0.5 is 6. That means if the volume goes down by a factor of 6, then that means the pressure has to go up by a value of 6, and C is the right answer. So if you have 0.1 moles of gas and it's got a volume of 22.4, then what is the pressure? We know that 1 mole of gas at 273 and 22.4 liters is 1 atmosphere, because that is standard temperature and pressure. So it's a definition. So if you have 1 mole of gas and it's 22.4 liters and 273, we know that's 1 atmosphere. So what if we have 0.1 moles of ethane gas? This goes back to Avogadro's law. So if it was 1 atmosphere with 1 mole, then if it's 1/10 of a mole, then it should be 1/10 of the pressure. So the correct answer here would be 0.10 atmospheres. Sometimes they'll give you a bunch of numbers and you'll think, ooh, wait, this is a math question. This is going to be hard. When it's not a math question at all. If you had 2 samples of gas in 2 different containers and each one had a small opening, which of the gases will escape faster? Well, this comes back to that whole idea of KMT. So if they're at the same temperature, that means they have the same kinetic energy. So we're not worried about temperature. We're worried about who is the fastest molecule. Whoever the fastest molecule is, it will escape the fastest through the pinhole. So you would need to go to your periodic table and you would need to look up the molar mass of krypton and the molar mass of radon and the molar mass of radon. You'll find that krypton is a smaller gas. And we know that the smaller gas has to be going faster to have the same kinetic energy. So we're looking for something like krypton will escape faster. And that's both A and B. So which answer is wrong? Well, B says because its initial pressure is higher. But we know that they're both the same volume, and they're both the same temperature, and they're both 0.1 moles. And if all those things are the same, then the pressure must be the same as well. So B cannot be our answer. But A is the correct answer because krypton atoms are moving at a higher average speed because they're smaller in molar mass. So here's a calculator question that you might find. If you have 2.2 grams of CO2 and 4 grams of argon, what is the total pressure in the container? We're going to be using PV equals nRT. So we need to know the V, the volume. We need to know the R value, which you can find on your reference sheet. And we need to know the temperature in Kelvin. So let's first work out how many moles of gas each one has. So if we take 2.2 grams and we divide it by the molar mass, we get 0.05 moles of CO2. If we take our 4 grams of argon and we divide it by its molar mass, we get 0.1 moles of argon. That means total we have 0.15 moles of gas, the argon and the CO2 together. So if I plug that into PV equals nRT, then, and I solve for P, then I'll get the setup on the bottom and I get the answer 3.43 atmospheres. Here's an example of an FRQ that you might see. And these FRQs are not just about gas laws. Notice that they're starting to tie together all of the concepts in Unit 3. So, describe the effect of raising the temperature on the motion of the CO2 molecules. Well, we know that a hotter molecule is a faster molecule. So, describe the effect of raising the temperature. A higher temperature would mean a faster molecule. Calculate the pressure of the CO2 in the container at 425 K. So we know the original temperature is 299, and we know the original pressure is 0.7. And notice we're here where it says rigid container. That rigid container means it will not change in volume. Rigid means it's like a steel can, and it's not going to get any bigger or smaller. So if you knew the original pressure at 0.7 and temperature, you could plug that into the combined gas law. P1V1 over T1 is equal to P2V2 over T2. And your T2 here is 425. And you don't have to plug in a volume at all because the volume is constant. It's a rigid container. In terms of KMT, explain why the pressure changes as it heats to 425. This goes back to that box I showed you before where we had the gases inside. So why would the pressure go up? Well, we know that hotter molecules are faster molecules, and when faster molecules strike the sides of the container, not only are you going to get more collisions more frequently because they're moving faster, they're also hitting with more force. And finally, they measure the actual pressure in the container at 425, and it's less than what the ideal gas law says. It's less than what the ideal gas law says. So why would this happen? This goes back to is it a real gas or an ideal gas? And remember, that only has to do with those intermolecular forces. So if you had CO2 molecules that were sticking to each other, then if you had the CO2 molecules that were sticking to each other, then that means that there are actually fewer molecules striking the side of the container. So let's see what they took as an answer. For choice A, the average speed increases as temperature increases. Notice it said describe, not explain. So all you're having to do is just say, this is what happens. Calculate the pressure. They're using the combined gas law, but they left out volume because you don't need it. They plugged it in and got 0.99 atmospheres, and that would earn you 1 point. In terms of kinetic molecular theory, explain why. Notice there's 2 different ways to get this point. Faster molecules collide more frequently because they're moving faster. Or faster moving molecules collide more forcefully. Now, if you name both, you wouldn't get both points because there's only 1 point here. But in my classroom, you probably would have gotten 2 points because that's a great answer. And then finally, why is it less than the pressure predicted by the ideal gas law? Why is that real gas different from the ideal gas? And that's something about the attractive forces. The attractive forces mean there's a lower pressure. Believe it or not, this is a question that they asked a couple years ago, and they said, hey, here's a liquid. It looks like a bunch of wedding rings. It looks like a bunch of engagement rings. So you've got the ring with the diamond on it. If that's what it looks like in the liquid state, then what would it look like in the gas state? So you could draw in box 2 what you think the molecules look like in a gas state. And we know a liquid tends to puddle together at the bottom, and they're kind of stuck to each other. But we know in a gas, those molecules are actually taking up the whole volume of the box. So you'd want to draw those molecules in the whole volume of the box, and you wouldn't want them stuck just together in one corner. The other important thing is you want to make sure they still look like engagement rings, because when we boil something or when we change it to a gas and do a phase change, we're not changing those intramolecular forces, the things inside of the HBr. We're only breaking those forces between HBr molecules, those intermolecular forces. So hopefully this is giving you some insight to what gas law questions would be like on the AP exam. So realize that some of it's math, but a lot of it is really a deep understanding of how do molecules and atoms interact with each other. And that builds on those periodic trends that we talked about, and it builds on the Lewis structures that we talked about, and it also builds on those very important intermolecular forces that we did in the weeks before this. All right, y'all have a great day, and I hope you learned something.